Welcome to part 2 of the lecture on the SSA form. Well, let us recapitulate a little bit. So, a program is said to be in SSA form if each use of a variable is reached exactly by one definition. The flow control remains exactly as in the non SSA form, but there is going to be a special operator called the phi operator, which is introduced into the join nodes. The phi operator is useful for the selection of values in join nodes. So, there may be, because we have a condition that there is exactly one definition for each use, there may be many definitions of the same variable reaching a point, and which one to choose is the question. So, this is resolved by the phi operator. Not every join node will need a phi operator. If the same value is coming through all the paths, all the edges into a join node, then we really do not need a phi operator there. Here is an example of a non SSA form and the SSA form. So, here this is the non SSA and this is the SSA. So, you can see that there are two definitions of I coming here, one is coming this way and the other is coming this way. So, we have a phi operator for I, and similarly there is a definition of n coming into this, and then these definitions of n are again entering this. So, we have a phi operator for n here, and then here is a phi operator for n because of these two definitions coming in. So, these are the salient points of an SSA form. The semantics is simple. So, when the phi operator is supposed to execute, depending on the arc through which this node is entered, the appropriate parameter is chosen. For example, if we enter through this, then the first parameter is chosen, and if we enter through this, the second parameter is chosen, and that is assigned to the left hand side. There are some conditions on valid SSA forms. So, the first one says if two non-null paths from nodes x and y each having a definition of v converge at a node p, then p contains a trivial phi function of the form v equal to phi v comma etcetera. And each appearance of the variable v in the original program or a phi function in the new program has been replaced by a new variable v I, leaving the new program in SSA form. So, in other words, renaming of variables in this trivial phi functions and otherwise have been performed already. So, the values of the new variable and the old variable must match, that is what the third condition would say. Now, condition 1 also says the assignments to the phi functions will also qualify as assignments to the same variable, and therefore, they may in turn introduce more phi functions. So, the dominance frontier really tells you exactly where phi functions are to be included, including the recursive nature of this condition 1. So, here is an example of the computation of dominance frontier. So, intuitively dominance frontier is the set of nodes for a particular node, it is a set of nodes which are just beyond the region where the node dominates. So, for example, this node and this node they dominate all other nodes. So, for example, start dominates all nodes. So, there is no other node to which we can reach. So, its d of function is phi, whereas let us look at B 3. So, here is B 3 and then it dominates B 5, B 6 and B 7. So, B 5, B 6 and B 7, and after passing these, the next node that we come to is B 2. So, B 2 is on the dominance frontier of B 3. So, this is the meaning of the dominance frontier, and its use is it tells you exactly where phi functions are to be introduced. If we consider those nodes where the assignment statements exist. Here is another example which is very similar. So, if you consider B 5, so B 5 is here before then B5, B6. So, B5 really it dominates B6 and B7 only. So, the next node we come to is B8, that is why B8 is the dominance frontier for B5. So, the algorithm is straightforward. We looked at this algorithm in the previous lecture already. We always start from a node whose the predecessor of a node, and then go on climbing in the dominator tree until we meet the immediate dominator of that node. So, this is the algorithm. Now, the first step is placement of the phi. So, this requires computation of the dominance frontier of each node in the flow graph. So, for the phi placement algorithm, we pick the nodes n I with assignments to a variable, then place trivial phi functions in all the nodes which are in the dominance frontier of that node, and then to do this we use a work list. So, this is how a program would look like after placing trivial phi functions. The arguments are not yet renamed, the variables are not yet renamed, everywhere it still remains as I equal to n equal to etcetera, etcetera. So, let us look at the place phi function the program and quickly and see how it runs. So, this is executed once for each variable in the flow graph. So, has phi is true if a phi function has already been placed in a basic block B. So, process B is true if V is is true if B has already been processed once for variable V. So, these two are set to false and initialized for the whole program. Now, the work list W is made empty to begin with, and we add all the assignment nodes which are nothing but the set of nodes containing assignment statements assigning to the variable V to this particular work list. So, we say processed B equal to true and add that to the work list. So, now in the loop we remove a node from the work list, then take the dominance frontiers of that particular nodes in the dominance frontier of that particular node, and then if a phi function has not been placed in that particular node y, we place one and then make has phi true, and if the new node has not been processed yet, then we add it to the work list and set process as true. So, this is the one which takes care of the recursion in and make sure that addition of new phi nodes which may result in addition of some more phi nodes is taken care of. So, after the phi construction process is over, we need to rename the variables. So, for example, this is the final form that we need to produce I 2 equal to phi of I 3 comma I 1 etcetera, etcetera. Similarly, in this example as well. Okay. So, we are going to refer to these examples as and when necessary. How does the renaming algorithm work? So, first of all, the renaming algorithm performs a top down traversal of the dominator tree. It does not travel along the flow graph, but it traverses the dominator tree. So, whenever it goes to a particular node in the dominator tree, it processes that particular node in the flow graph. It uses a pair of version stack and version counter. So, this is one pair. For each variable you have a pair of this kind. So, the top element of the version stack V is always the version of the variable that we have to use. So, in other words, there will be versions of variables V 1, V 2, V 3, V 4 etcetera, etcetera. So, as we get a new definition for the variable in the program, we are going to use a new version for that particular variable. But the reason why we require the stack is that the variable which has been renamed must be used for all the uses of that particular definition. Okay. So, it is not enough to just rename the definitions, but we also need to rename the uses, and that must be done for the particular definition and its uses. So, the top element is always the version to be used for a variable usage encountered in the appropriate range, of course. So, here the counter V is used to generate a new version number, that is it. So, we are going to show the algorithm for a single variable, but a similar algorithm is executed for all variables. Yeah, we just have to use an array of version stacks and array of counters. There is something very important here. First of all, we still have not explained why we need to do a top down traversal of the dominator tree. The important property that an SSA form should satisfy is called the dominance property. The definition of a variable dominates each use. So, all the uses of a variable are dominated by those nodes are dominated by the appropriate definition. When otherwise, if we are looking at a phi function, then the definition of a variable dominates the predecessor of the use. So, this is the way it is. So, this is called as the dominance property. So, because of this, it is apt to say that the renaming algorithm performs a top down traversal of the dominator tree. So, how does it do it? Once we want to actually process the uses after we meet the definition, and because the definition dominates all its uses, we must process the definition first, and we can do it by traversing the dominator tree from the top. So, renaming for the non-phi statements is carried out while visiting a node, particular node n, whereas renaming parameters of a phi statement in a node n is carried out while visiting the appropriate predecessors of n. This will become very clear now as we go along. So, let me show you an example first and then go back to the algorithm itself. So, let us run through an animation of this program. So, here is the start node will be processed to begin with, and then it leads to basic block B 1. So, in the basic block B 1, we first rename the definition I 1, and then read n 1 is also a definition. So, that is also renamed. And then when we are visiting B 1, we also have to look at the phi functions in the successors of this particular node B 1. So, that is in B 2. So, we are going to rename the appropriate parameter corresponding to I 1, that is the second one, because it is the second arc that is coming into the node B 2. So, I 1 this I from the trivial phi function is renamed as I 1, and this n is renamed as n 1, that is all. Nothing else happens during the visit to B 1 apart from renaming I 1 and n 1 here. So, next B 1 dominates B 2. So, the next node we visit is B 2. So, now here we are renaming I 2 and n 2, these are the two definitions, these are two new definitions of I and n respectively, and nothing happens as far as the first two parameters of the phi function, they remain as I and n. These will be renamed when we are visiting the node B 7, which actually has an incoming arc to B 2. So, this is a usage of n. So, and this is supposed to be n 2. So, we make it n 2 and that is all there is to it. Then B 2 dominates B 3. So, we go to this is a usage. So, the appropriate obviously the definition is n 2. So, this is named as n 2. This is where the version stack comes into picture. The topmost entry will have n 2, n 1 is below that. Then after B 3 we come to B 5. So, it is a depth first search kind of a traversal. So, when we rename n 3, before that we rename n 2, because n 2 is a usage corresponding to the old variable n 2. Now, there is a new definition n 3. So, we now n 3 is feeding into B 7 and that is the first edge. So, the parameter of the phi function in B 7 is renamed here as n 3. Okay. Then B 6 is traversed and that would rename n 2 and n 4 appropriately. So, see here that this is n 3, but for this it will be a new definition called n 4, but the usage here comes from this n 2. So, this is still n 2. So, here we have the incoming edge as the second one and N 4 is renamed here. Then we go to B 7 and here we rename N 5 and I 3, right, and then I 2 will be renamed based on this particular definition I 2. The version stack being different, this I 2 would have been in a different stack altogether, and that is easy to use here. And this edge is coming into B 2. So, the first two parameters here are renamed as I 3 and N 3. Then we process B 4, rename this as I 2, and finally, we stop. So, this is our sequence. So, let us go through the algorithm and see how it works. So, function rename variables. So, here is the top of version stack to begin with will be empty. So, this will act as the kind of if the top the function when the stack V is empty, then this will be the bottom of stack marker, and if this is reached, we are going to stop, otherwise stop. Otherwise, somewhere in the middle, this will be the most current version that we want to use. So, for all statements S in B do. So, let us look at the main calling program to begin with. So, for all variables x in the flow graph do. So, the version stack is empty, version counter is initialized to 1 and we push 0 onto V. So, this is the end of stack marker, and then we call rename variables x comma start. So, that is where we come here. So, the stack is empty to begin with. Now, for all the statements S in B, so we have a basic block. Right now, if it is start, there will be no statements in it. So, none of these will be executed. So, for the first start block, nothing is executed here, nothing is executed here, and none of these are executed. Then we come to this, for all children C of B in the denominator tree do call rename variables. So, we are going to call on B 1. Okay. So, start did nothing, we go to B 1. Now, we come here. So, we have B 1 and the stack still contains only the top of stack marker, but there are statements S in B. So, S is a non-phi statement here, I 1 equal to 0 and read N 1 are both non-phi statements. So, replace all uses of x in the RHS with the top of V. There are no RHS variables to be renamed here, there is nothing at all. Okay. Now, therefore, nothing is done here, if S defines x. So, basic block B 1 has two assignment statements, read is also an assignment. So, I equal to 0 and n equal to 0. So, replace x with x v in its definition. So, v is 1. So, we are going to have I 1 equal to 0 and push x v onto v. So, now the new variable which is generated, the version is pushed onto the version stack, appropriate version stack. Remember that there is one version stack for each variable. Okay. So, I 1 is pushed onto I stack and n 1 is pushed onto the n's stack. So, now increment the version counter appropriately. So, version counter and n's version counter are incremented as far as B 1 is concerned. Now, look at the successors of the basic block. So, this is the successor B 2, it has a phi function, that is what we want to see. So, J be the predecessor index of B with respect to S. So, that is we are looking at which particular arc this is, the first arc or the second arc, that is the J that we are considering. So, for all phi functions f in S which define x do. So, we are looking at the phi functions in this successor I and n. Okay. So, replace the jth operand of f with top of v. So, appropriately here we are going to replace this with I 1 and this with n 1. So, the replacement for phi functions is over. Now, this process continues with the other children of the basic block B. So, in this case from B 1 we call B 2 and then B 3 etcetera as I explained. So, once all the children have been exhausted. So, we the version stack is popped until it reaches the element V, which we actually read here from the top of the stack. So, we enter the function with a particular version variable, and then we also exit that function with the same when we reach the same configuration of the stack. So, this is how renaming of variables happens. So, to summarize, within a block we first look at the RHS and rename variables, then we look at the LHS and rename the variables, then we look at the successors of the basic block and rename the 5 function parameters appropriately. So, this whole thing happens during a traversal of the dominator tree. So, now this is the final rename product after renaming. So, this would have been taken care of. Okay. The next issue that we need to worry about before we look at optimizations for various optimizations of various kinds is that the 5 functions cannot be executed on a machine. So, that is a concern. We must translate the 5 function to appropriate machine code. So, how do we do that? So, there is a fairly straightforward scheme. So, if you recall, we would have had a phi function here, max phi equal to phi of max 1, max 2, max 3, max 4, right. That is what we would have had. So, now we introduce a temporary t, copy max 1, max 2, max 3, max 4 in the appropriate predecessors to t, and then say max phi equal to t. So, this scheme will always work. We need to apply another set of transformations on it later on, for example, copy propagation. So, this will become a max 1 equal to a and t equal to max 1. So, this becomes t equal to a and so on and so forth. So, apart from that, this scheme will work. Some other scheme which one can think of sometimes does not work. Let me show you an example. Here is a program in the SSA form, x 1 equal to 1, x 2 equal to phi of x 1 comma x 3, x 3 equal to x 2 plus 1, and then there is if p then branch, otherwise go out. So, instead of generating a temporary t and then saying along this path t equal to x 1 and then along this path t equal to x 3 and so on and so forth, let us try to be cleverer and then straight away write take this variable x 2 and assign it x 1 here. Okay. Instead of t equal to x 1 and then x 2 equal to t here, we said x 2 equal to x 1 directly. So, this statement is not needed anymore, because we are making an assignment to x 2 equal to x 1 here, and we will have to make an assignment x 2 equal to x 3 just after this statement x 3 equal to x 2 plus 1, because why? That is because this arc will be taken only after one iteration. So, let us go through one iteration, execute x 3 equal to x 2 plus 1 and then say x 2 equal to x 3, but this is a wrong translation. So, this will not do at all. See, this is x 2 equal to x 1, then you have x 3 equal to x 2 plus 1 and then you have x 2 equal to x 3, then you go back. So, this gives you an incorrect translation, because the first time you come here x 2 should have taken the value x 1, right, and then if we do not iterate and then return, it would give you x 2, whereas here we said x 2 equal to x 1. So, x 3 is equal to x 2 plus 1, therefore, now x 2 equal to x 3 makes the value as x 2 plus 1. Okay. So, whereas in the previous program it would have been x 2 equal to x 1 if we did not iterate at all. So, the value returned here is one more than what it would be returned here if we did not iterate through this particular program. So, in other words, it always even if we iterate, it will always have one more than the previous version. So, this is a wrong translation. So, the correct translation is exactly the way I showed you. Take a temporary, assign it to assign x 1 to it, and then take a temporary, assign x 3 to it. Okay. So, here x2 retains x2 equal to t. So, here x3 equal to x2 plus 1 and then t equal to x3, but if we go through without any iteration we still return x2 which is the old value. Okay. So, the new value is not used immediately. Okay. So, this actually is the correct translation. So, let me show you another example of what can go wrong. So, we have the original program here x equal to y equal to and then we are swapping. So, we simply swap in a loop. Okay. So, again and again and again, that is all, t equal to x, x equal to y equal to t. We convert it to SSA. So, now t actually gets a phi function because this x here can be from here or it could be from here, right. So, we have x naught comma x 1, this is x naught and y naught. Then x 1 also gets a phi function here because there are two values of y coming in, one through this and another through this. So, phi of y naught comma y 1 and then y 1 equal to t. So, this is the new y 1. So, y 1 equal to t. So, with this we can do a copy propagation because the t can be replaced by phi of x naught comma x 1. So, we have x 1 equal to phi of y naught comma y 1 and y 1 equal to phi of x naught comma x 1 and this is the correct SSA form, no problem. But then if we try to hasten and then say okay, let me do assignment to x 1 and y 1 right here and then immediately afterwards at this point the whole, like in the previous case we get a wrong answer, x naught equal to y naught equal to x 1 equal to x naught, y 1 equal to y naught, x 1 equal to y 1, y 1 equal to x 1. So, this obviously gets the same value into x 1 and y 1. So, this is wrong, it is not swapping at all. So, we need to introduce the temporary t 1 equal to x naught, t 2 equal to y naught, x 1 equal to t 2, x 1 equal to y 1 equal to t 1, t 1 equal to x 1 and t 2 equal to y 1. So, this is the correct translation and in this case you can't really do too much of copy propagation, a little bit yes, but not too much. Okay. So, y 1 equal to t 1 will and t 2 equal to y 1 will become t 2 equal to t 1, but beyond that not too much of copy propagation will happen here, but this is the correct translation. So, in other words, one has to be very careful and introduce temporaries in the predecessors of the phi function, so that appropriate translation takes place and then leave it to the optimizer to remove the copies if it can. So, what are the various optimizations which are possible with SSA forms? So, let us look at some of them. The first one is dead code elimination. So, dead code elimination is extremely simple. Why? Well, you have exactly one definition reaching each use, right. So, if the du chain of a variable is empty, then there are no uses of that particular variable and therefore, the definition has nothing, no effect, right, nothing to do. So, examine the du chain of each variable to see if its use list is empty. So, if it is so, remove such variables and their definition statements, as simple as that. If a statement such as x equal to y plus z or x equal to phi of y 1 comma y 2 is deleted, what happens? It is not that you can just delete the statement as such, but then there are definitions of y 1 and y 2. For example, y and z, x equal to y plus z may not have any use. In other words, I have not used x later on at all. But what happens to the du chain of y and z or y 1 and y 2? So, in that this statement will be present, right. So, we have to actually remove those statements from the du chains of y 1 and y 2 or the du chain of x. So, we must take care to do that as well. Otherwise, there would be a statement which is deleted, but is present in the du chain. So, some processing would actually issue some error. We can do simple constant propagation, we can do copy propagation, we can do conditional constant propagation, constant folding, global value numbering, etc., etc. So, let us look at each of these in sequence. So, we have already seen enough constant propagation. This is probably a much simpler version of constant propagation. The more complicated version called the conditional constant propagation we will discuss very soon. So, in simple constant propagation, you are only going to look at statements of the form x equal to c. Okay. So, wherever x occurs, we will try to replace it by c, that is what we want to do. So, for this again we are going to use a queue. Okay. So, this is called as a statement pile. So, this is initialized to S such that S is a statement in the program. So, you put all the statements in the program into the statement pile. So, while the statement pile is not empty, take a statement. If S is of the form, it is of the form of a phi statement, x equal to phi of c comma c comma c. So, in other words, all the parameters of the phi statement are constants. Okay. This need not happen right in the first instance, it can happen after some constant propagation is carried out. So, that means the same constant value is arriving through each of its edges in preceding edges. So, we can replace this comfortably by a statement x equal to c, no harm done. Then if S is of the form x equal to c for some constant c, delete the statement from the program, and for all statements in the du chain of x, substitute c for x. So, in the statement t, and then add t to the statement pile. Okay. So, in other words, what we do is we take the statements in the du chain, examine it, obviously there will be some usage of x there, and we remove that x from the statement, we put x in it, c in its place, the constant c. So, we have done constant propagation, replacing x by c by replacing that x by c, and now we need to process that statement as well. So, because that may lead to further replacements and things of that kind. So, we keep that on the statement pile and go ahead, that is it. So, this is a very simple constant propagation. So, the constant flows down the program. Now, the point is each statement which in which a variable is replaced by a constant may actually in turn induce other statements to become targets for constant propagation. That is why this is necessary. So, you may actually first time you visit a statement, there may be nothing to do, it may be of the form x equal to y plus z. But then it is possible there is y equal to c and z equal to c, and y plus z eventually becomes a constant. Okay. But we are not, this particular simple constant propagation is not very effective, because we are not even evaluating expressions here. Okay. Even if it becomes y plus z and it is c plus c1 plus c2, we are not evaluating here. So, the next version of constant propagation called conditional constant propagation will do not only this, but a little more. So, we will see that soon. So, what is copy propagation? It is very similar to constant propagation. So, a single statement single argument phi function such as x equal to phi y in or a copy statement x equal to y, we can delete it and y is substituted for every use of x. So, wherever we have x, in x equal to c, wherever we had x, we substituted by c. Here wherever we have x, we substitute by y. So, that is copy propagation, very simple copy propagation. So, now we come to conditional constant propagation. So, let us do a recap on the constant propagation framework that we studied some time ago. The constant propagation framework had a lattice for its variables. So, the variables could take three values. One was undef, that is to begin with they do not the variables do not contain any value. So, they are undefined. So, undef. The variables also could take any of the constant values assuming they are integers -3, -2 etc., or 1, 2, 3. These constant values are incomparable. So, this is the lattice that we have. So, all constant values are grouped as constant. Okay. So, that is the middle abstraction. Then the third abstract value is not a constant. So, we have determined that the variable is not a constant anymore. So, for example, for a particular node, the incoming predecessors give you y equal to 2 along one path and y equal to 3 along one path, another path, then y cannot be a constant at all. It cannot be a constant, it can either be 2 nor 3 or something else. So, in such a case y can be given the abstract value NAC, not a constant. So, if we have a statement x equal to y plus z, then here we have listed the effect of the transfer function for x equal to y plus z. As we said in the previous lectures, the product of these lattices, one for each variable, is the domain of data flow values for the constant propagation framework. So, here it suffices to see the transfer function effect. Okay. Suppose y takes the value either ndef or constant or NAC. Okay. So, that is what my gives you. Y would be the actual value, but my gives you the abstract value. Depending on what mz is, ndef, C2 or NAC, m prime x, the new abstract value for x would be either ndef, undef or NAC. In other words, unless it is all of them are constant C1 then C2, x will not be C1 plus C2. In other words, we start from the top and we can only go downwards and we never go upwards. Once we have determined that a variable is not a constant, its value can never change. But if the variable had an undefined value, it could become defined and carry a constant, or if it had a different constant value along two paths, it could become not a constant in some join node. So, you can only go downwards. That is what is shown here. If it is undef, then it is undef or NAC. If it is constant, then undef C1 plus C2 or NAC, but if it is NAC, then it can be nothing but NAC. So, we do not go to the top upward in the lattice. So, this is the constant propagation framework that we had already studied. So, we are going to use the same framework for our conditional constant propagation as well. So, SSA forms along with extra edges corresponding to the DU definition use information are used here. So, an edge from every definition to each of its uses in the static single assignment form, henceforth called SSA edges, is used here. So, actually we use both SSA edges and flow graph edges, and we are going to use two different work lists or queues, one for each. The flow pile is a queue corresponding to flow graph edges, and SSA pile is a queue corresponding to SSA edges. So, I must point out a difference here. In the simple constant propagation, if you recall, we went by basic blocks, okay, or the statements in the program, whereas in the case of conditional constant propagation with SSA form, we are using edges. Okay. So, unless we traverse an edge, actually the node which is the target of that particular edge is not reachable. So, that is the important point here. Flow graph edges are used to keep track of reachable code. So, as we go on, as we say each edge is visited, we can visit appropriate nodes as well. So, and the SSA edges are used for propagation of values. So, once we reach a particular node for the first time, we visit that particular node a second time only if some value which is feeding into that particular node changes. So, if that happens in the definition corresponding to that particular variable in the node. So, if that happens, then the SSA edge would be responsible for the flow of this particular information. So, we will this will become very clear as we go on. Flow graph edges are added to flow pile whenever a branch node is symbolically executed or whenever an assignment node has a single successor. So, this is very clear. So, if we have a single successor after finishing a particular node, the next node would be added. As I said, we are going to visit each node only once through the flow graph edges. We will be visiting a second time only if a value changes in that particular node. And in the case of a branch node, we are going to evaluate the condition in that branch node and then add either the true edge or the false edge to the work list appropriately. So, as SSA edges coming out of a node are added to the SSA work list whenever there is a change in the value of the assigned variable at that particular node, not otherwise. This ensures that all uses of a definition are processed whenever a definition changes its lattice value. So, this is how the SSA form becomes powerful. You are making sure that nodes which change values are processed, but if we do not use SSA edges to reach that particular node, we may have to go through many other nodes in the flow graph. So, traversal of the flow graph again and again would be necessary in order to actually process that particular node. So, if this happens, the amount of time that is needed for the algorithm actually becomes very high. Okay. So, that is the advantage we have in the case of conditional constant propagation with SSA form. The time needed to process the program, do the constant propagation is much lesser than the time needed to do constant propagation with conditional constant propagation with just the flow graph. So, this algorithm needs only one lattice cell per variable and not on a per node basis. So, previous versions of this algorithm which worked on the flow graph required actually one lattice per node per variable. So, there was too much storage necessary, and it also requires 2 lattice cells per node to store expression values, the old and new values of an expression. So, conditional expressions at branch nodes are evaluated, and depending on the value, either one of the outgoing edges corresponding to true or false or both edges corresponding to NAC are added to the work list. So, if only true part is true, only that edge is added. If only false part is holding, that edge is added. Otherwise, both edges are added to the work list. However, at any join node, the meet operation considers only those predecessors which are marked executable. So, this is important for a phi function, because in a phi function there are many parameters, each one corresponds to the preceding edge. So, we do not consider any of the edges which are incoming and are not marked executable. We consider only those edges which are marked executable. So, this makes sure that we catch more constants, some dead code and some unreachable code etc., are not handled or not are eliminated and so on. So, let me give you an example which is slightly away, but it is okay, we will come back. So, here is the example. So, here is the program, very simple program, start A equal to 10, B equal to 20, then there is a test, is B equal to 20, yes, A equal to 30, no, we go straight. If it is after assigning a equal to 30 here, we say c equal to a and stop. So, this is easy to comprehend, and at this point after a equal to 10 and b equal to 20, obviously is b equal to 20 is true. So, only this branch will be executed at runtime. Now, we assign a equal to 30. So, this branch is never executed and we come here. So, C d equal to a will make the value of d as 30 and then we stop. So, this is the original program. So, here is the SSA form. So, we have there are 2 assignments to a. So, we have a1 and a2. We have just one assignment to a. So, we are just going to retain it as one assignment to b. So, we are going to retain it as b, only one assignment to d. So, this will be retained as d. So, a1 equal to 10, b equal to 20, then is b equal to 20 the test, then this becomes a2 equal to 30, and here we have a phi function a2 along this path and a1 along this path, then d equal to a3 and then stop. So, the solid edges are all flow graph edges, and now this a1 is used here. So, this is an SSA edge, this a3 is used here. So, this is an SSA edge, and this a2 is used here. So, this is another SSA edge. Actually, we should have shown more SSA edges here, but just to avoid clutter I did not do it. So, this is b equal to 20 and is b equal to 20, there is a usage here. So, this will be another SSA edge. So, how does the CCP algorithm work? So, you start with start, nothing happens, then you have a1 equal to 10. So, you do a symbolic execution. So, now the value of a1 is from undefined it changes to 10. So, this SSA edge actually is added to SSA pile. Okay. Then we go to this. So, the statement b equal to 20 when executed will change the value of b from undefined to constant 20. So, this will change the value of b, the lattice value changes from undefined to constant. So, this SSA edge is also pushed onto the stack, right. So, now after that we come here, we check. So, this edge was added to the the flow pile to begin with, and then we added this edge to the flow pile. Now, we added rather the SSA pile. So, this edge was next added to the flow pile. Now, this edge was also added to the SSA pile, but it suffices to say that these two SSA edges have no effect at this point. Why? When we look at this parameter a1, this node has both its preceding edges as non executable, they are not marked executable. So, there is nothing we can do here. So, and this particular SSA edge has no effect, because once we before reaching this node, this cannot be used, because this edge would have been marked not yet executed. But once we execute it, this SSA edge is of no use again, because the value does not change any further. We have processed it once and we are not going to process it again, unless b equal to 20 changes to b equal to 30 or something like that. So, this is the next step. Then we take this edge, okay. Why? B equal to 20 is true, b has a value 20, symbolic execution checks 20 equal to 20. So, this is true. So, only the true edge can be taken. So, we take the true edge. So, this will be put on the flow pile, right. So, then we check in the next step, we check, okay, is a2 equal to 30, so sorry, the assignment a2 equal to 30. So, the value of a2 changes from undefined to 30. So, now when we again the value has changed and this goes on to the SSA pile. Okay. So, then we come to this via this particular edge. So, this is put on the flow pile. So, when we take out this edge, this node will be executed. So, this particular node, when we come here, please observe that this particular edge is not yet marked executable. So, we are not going to actually consider this edge when we consider the phi function here, we are going to consider only this particular edge. So, this will be ignored, that is why the node is written as A3 equal to phi of A2. So, once we evaluate this phi, it is very easy to see that this edge was taken. So, it is A2 and value of A2 is 30. So, A3 equal to 30 is the statement to be executed next. So, then once we do that, A2 equal to 30 is executed, and then D equal to A becomes A3 becomes D equal to 30, and then we stop. The SSA edges in this particular example do not play any significant role, but in the second example they are going to play a very significant role. Let me show you the second example also, and then we will go on to the algorithm itself. So, this is a slightly more complicated example. So, we have A1 equal to 1, B1 equal to 1 and C1 equal to 0 here. Then we have B2 equal to phi of B4 comma B1, C2 equal to phi of C4 comma C1, and if C2 is less than 0, etcetera, etcetera, etcetera. If B2 less than 20, B3 equal to A1, etcetera. False, we come to B5 equal to C2, and then these two merge and there is a loop. So, this is our example. We start and then we execute this node. So, A1, B1 and C1 change their values to these constants. Then we have to execute this particular node, because this edge will be added to the flow pile. So, remember that because this particular edge is not yet executed, we actually will consider only this edge and the parameter corresponding to it. So, that is the second parameter. So, phi of B1, there is only one now. So, phi of B1 is trivially B1 and that value is 1. C2 is phi of C1 and that value is 0. So, now if C2 less than 100 becomes true, because C2 is 0, 0 less than 100 is true. So, we only take the true edge and come to this. So, this particular node will be executed next. So, B2 less than 20 is also true, because B2 is 1, 1 less than 20 is true. So, we take only the true branch. Remember that the false edges are not yet marked as executable. So, once this is marked as true, we come to this node. So, this becomes B3 equal to A1 and C3 equal to C2 plus 1. So, we get B3 equal to 1 and C3 equal to 1, taking these constant values along the way. So, that again leads us to this particular node, this is not yet marked. So, remember that. So, therefore, we do not consider this particular edge when we take the phi function, we consider only this particular edge. So, there is only one parameter, that is B3 and another parameter C3 for the second one. Here phi of B3 again is just B3. So, value of B3 is 1. So, B4 gets a value 1. Phi of C3 is C3, C3 has a value 1. So, C4 also gets a value 1. Now, this edge is now marked executable, and this is a second visit for this particular node, that is why this has been shown in a different color. So, the previously it was so, now this edge is also marked as executable, this edge is also marked as executable. So, what happens? Phi of B4 comma B1, B4 has a value 1, B1 has a value 1. So, phi of B4 comma B1 is phi of 1 comma 1. So, that is okay, that is still a value 1. But if you look at C2, it was previously a constant value 0. Now, phi of C4 comma C1, C4 is 1 and C1 is 0. So, along one path you have a constant value, along another path you have a non-constant value. So, now C2 takes a value not a constant in AC, and therefore, C2 less than 0 becomes unknown, and we need to add this edge also. In the previous case, this edge was not yet executed. So, now we mark this also, put it on the work pile. So, we need to, this part is not yet marked. So, we are not going to execute this, traverse this edge again and again, unless the value changes. The value has changed here. So, C2's value has changed, B2 has not changed. So, the usage of C2 is here in this. So, we are going to actually process this B5 using this SSA edge now. So, no change in the value of B2. So, now C 3 changes value from 1 to not a constant, because C 2 is not a constant. So, this C 3 has changed a value, it has changed from 1 to not a constant. So, this SSA edge is also going to be added to the SSA pile. So, now with this there is no change here. For example, there is no change here, B 4 and C 4 do not really change any. So, okay. So, we cannot, we do not have to, sorry, we do not have to execute this particular node again and again, because B 5 is here. So, only this particular value which has changed will be used here. Okay. So, this edge has not been executed at all, but C 4 has changed the value. Okay. So, now nothing happens in B 6. So, next is this particular node which is used. So, this particular change in C 4, this is this is not a constant really. Okay. So, this change in C 4 will introduce some changes in this, supposed to introduce some changes in this, but it does not. What see? So, this has become not a constant, it has actually gone to this, but C 2 does not change anymore. Okay. C 2 was not a constant, even though this C 4 now changes to not a constant, this SHA edge does not change the value of C 2. So, this part does not help, because this is not yet executed. Finally, this is a third visit to B 2, no change in either B 2 or C 2, and algorithm stops. So, this is the place where the algorithm has stopped, and this shows that after the first round of simplification we get this flow graph. I am going to show this flow graph in the next lecture as well. So, finally, we have B 2 equal to 1, C 2 equal to phi of C 4 comma C 1, C 2 less than 0, etcetera, and after some more simplification the flow graph becomes like this. So, we will discuss this example with along with the algorithm in the next lecture again. So, thank you.